Dear students, in this video, I will explain how to make this one, flower vase. So tomorrow we are going to work with that one. We are going to analyze the flower vase, okay, flower vase. So it's very simple to make this one, okay? So very simple. Maybe within 5 minutes you can make. So if you know the coordinate points, here coordinate points are directly given, okay? So just create a coordinate points and just use spline, okay? Spline, connect using spline. I'm going to explain this one using ANSYS as well as using CATIA also, okay? So you can model this one using CATIA or you can model this one using ANSYS. So I explained both of the softwares, okay? How to make using ANSYS and CATIA. So first create using CATIA, start shape, generative shape design. So because we are making 3D surface body, okay? So flower vase. So create points first. So x coordinates 50, y 0, 0, okay? Z 0. So wait, here we can create point. So wireframe toolbar, you have, right? Wireframe toolbar like point, line, okay? So point, line, plane, and all this point. You can double click to create multiple points, okay? Or so x coordinate is 50 millimeter, y 0, 0, z 0, okay? Click. That is first point, and again create point. 90, 40, 0, 90, 40, 0. So I double click, okay? Double click. 60, 120, 0, 60, 120. So it's lies in XY plane. So third point created, 40, 180, fourth point, 40, 180. And the final point is 80 to 80, 0. 80 to 80, 0. Click on OK. So yeah, we have 5 points. So now, so we have to construct a spline. So this one is like a spline, right? So we don't know a definite shape. It doesn't have circular or something like a spline. So spline is like a curved line. So how to create spline in that one? Use this one, okay? KTA. So spline. So point, select first point, second point, third point, fourth point in the order. Same order we have to use, okay? First point, second point, third point, fourth point, and the fifth point, okay? That is spline. It's finished. Okay, spline, okay. We can also create XY plane and create points, okay? And also you can use spline in XY plane. But this one is 3D spline and 3D point, okay? Method. So that is also possible. And after that one, I created and we use revolve. This one also surface body. Revolve. Where is revolve? Where is revolve? Here. Revolve. Yes, profile is this one, spline. And revolution axis is y axis, okay? So right click here, y axis. And 360 degrees. So by default, it's 180 degrees. 360 degrees revolution. Okay. And also at the bottom, we have to fill that one. Bottom is empty. We have to fill that one. So fill that surface, okay? Fill that surface. Fill that surface. Click on OK. And so these two are different surfaces now. So we join these two surfaces. You don't need to join, but better to join in order to make thick surface. Okay. We also use thick surface for 3D modeling. Just this one is for 3D solid modeling, 3D surface modeling, and you can analyze this one using 3D surface modeling and 3D solid modeling. Okay, I will explain what is the difference between these two tomorrow. Okay, yeah. So click on OK. Yeah. So that is surface body. So anything else? So nothing. Okay. And file, save as flower vase, KTF part. If you want to edit that one in future, we have to save that one as a KTF part. And again, in order to read from ANSYS, save as STP, flower vase STP. So just I use 3D surface model. Surface model. Okay. So close that one. The same thing, we can use ANSYS also. So same way, ANSYS also just create points and use line. So here, design modeler, ANSYS geometry. And I am going to work with design modeler. ANSYS new design modeler, geometry. Analysis stripe is 3D here, 3D, not 2D. 2D is only for plane stress and plane strain analysis. It takes some time. And here you can create point, construction point, okay? Construction point. So here one point, here another point. Oh, okay, change the units before, units in millimeter, right? Right now I don't know what is the unit. Okay. Delete. So Control Z, use Control Z. And the units are in millimeter. Is 30. Okay, again construction point. Start from before, set the units in millimeter and use this one. Use this one. Zoom all, okay? Otherwise, yeah, construction point, here one point, here another point. Yeah, B point is somewhere here, C point is here, okay. D point is here, and E point is here. Now we have to adjust the dimensions, okay? You can also use 3D point, okay? 3D point and 3D spline, but so what is H1? X coordinate. X coordinate is 50. So H2 90, H3 60, H4 40, and H5 80. So those are X coordinates, and Y coordinate is already 0. Second point, where is the second point? Here. Dimensions, vertical dimensions. This is second, right? I don't know which one is second, which one is first. Okay. Okay. Anyway, V6 40. And B point 120. 180. 280. So is it correct? Let's see. Okay, shape. Okay, it's correct. Yeah, now again same as in Ketia we did, right? Draw spline. Okay. So starting from here, I don't know if 3D spline is available in ANSYS or not. Okay. Yes. So open end means up to here. Okay. And again, draw line. Okay. So line, join first line and first point from here to here. Okay. So, but here, I am not sure this spline created by ANSYS or spline created by Ketia, both are same. Maybe there is a little bit difference because the programs are different. Okay. So the spline middle coordinates are different based on the program. Okay. We have some program. Okay. Some interpolation techniques and all, but I don't know. Both are same. Okay. After that one, go to modeling and create revolve. Okay, revolve. So select sketch 2, apply. Okay, geometry is sketch 2, and the axis is what? Axis is this one, vertical axis. Apply, and 360 degrees, add material, generate. It should create a surface body. Okay, surface body. So the problem is when you join these two, this and okay, the problem with ANSYS is when you join the end points. Okay, if you, I didn't join, I joined just only from here because there is a bottom. But if you join this one also, it creates a solid body. Okay, be careful. So it's a not solid body, surface body. You should create surface body. Okay, so like this one. So if one end is empty, we can see that one as a surface body. So that is the surface body. So click close. We finished the modeling. So you can either use the Ketia or ANSYS. Okay. So below joints, I did not explain using ANSYS because that one is a little bit taking time. Okay, using ANSYS. And that is also not difficult if you use ANSYS. Okay, that is end of this lecture. Dear students, we already modeled flower vase, right? So flower vase using CATIA, okay, using CATIA, and also we use ANSYS. So just create points and create line, okay, spline, and revolve this one that gives the surface, okay, of the flower vase. So in this video, I will teach what are the stresses developed inside the flower vase, okay, inside the glass material, when the flower was filled with the water, okay, up to here. So 100 millimeter below the water surface, that is given in the problem, okay. So water level reaches 100 millimeter below the opening of the vase. So water is filled until here. I want to solve this problem. So when water is filled, any fluid is filled inside some container. So because of the weight of the fluid, there is a pressure created on the walls of the container. That pressure is known as hydrostatic pressure, okay. So that at the side walls and at the bottom walls also. So because of the weight of the fluid, okay. Here you can give hydrostatic boundary condition, okay. Hydrostatic pressure boundary condition in ANSYS directly. You don't need to worry about all the details, okay. Just give how much the fluid is density, and fluid density is water, right? Water density is 1000 kilogram per meter cube, and the level of the fluid, how much it is full until this one. So this condition we have to give, okay. So we already created surface model, so we can use shell element to model this one, and also you can consider real 3D model, okay, not surface model. Surface model is just a surface body, but if you use a 3D body, okay, this 4 mm thickness, right? Yeah, 4 mm thickness, 4 mm thickness. So if the body is 4 mm thickness, and if you give thick surface to this one, and that one becomes a 3D body, okay, not a surface body, 3D body. So you can also work with the 3D body. Why we are working with surface body? Because to save time, computational time. So surface body is just only one surface, and we use shell elements, right? And if the thickness is very small, we can use shell element. It's a curved shape, right? So let's open the workbench. So after opening the workbench, we open the static structural, simple static structural. And we have to change the engineering data here because the material is glass. E is 70 GPa and 0.17. Okay. So change the engineering data values, double click, and you can change the Young's modulus. Okay, rename this one to glass. I'm just using the same, all the properties are same as structural steel except the Young's modulus. Young's modulus is 70 GPa. 70 GPa means 70 E9. And Poisson's ratio is 0.17. 0.17. So you don't need to change anything, okay? Only these two values. So Young's modulus and Poisson's ratio. So because this glass body is subjected to only hydrostatic pressure. Suppose it is a rotational body, something rotating, you have to change the density also because mass is different, right? And also if it is subjected to some temperature change, so thermal stress analysis, we have to change this one also. But right now we don't need to change, okay? just change the Young's modulus and Poisson's ratio values. Okay. And geometry, and I already created geometry. So import that geometry, surface model, browse. Where is the so flower vase 3D surface model? So that is in, I already provided this file, geometry file. You can download and import here. Okay. So you can work from here. And model, yeah, first let's check how it is imported. It is geometry in design modeler. Import and generate. So 140 and one more. So this one is flower vase. Okay. Okay. After that, close this one. And model, you can give thick surface here or here also in model. And we are working in 3D, right? Not in 2D. This is a 3D surface body. So edit. So only thing we have to give here is this one is fixed support, because flower vase is fixing, placing on table, right? So this dimension is not changing. We can say that one is a fixed support, and another one is hydrostatic pressure on the side walls. Okay, hydrostatic pressure mean fluid boundary conditions we have to give. That's all. And we have to choose the element type. Okay, so element type. So by default, ANSYS assigns some element that may not be that may not give the correct result. Okay, you can change that one later. So flower vase here, there is a question mark here because we have to provide thickness for this surface body. Okay, shell element thickness 4 millimeter, that is given in problem. So make sure that here in millimeter, suppose here in meter, should be careful, we have to give 0.004. Okay, so be careful with the units. So 4 millimeter. Okay, and yeah, update. So this one is default mesh. Okay, so first I just solve using default mesh. This one is default mesh, so very big mesh. It's a combination of quadrilateral element and triangular elements. Okay, so and it gave very coarse mesh. So yeah, and fixed support is bottom. So select the face filtration, and you can select from bottom or top. That doesn't matter, because this one is a shell element, right? Shell element. Usually it is you. Okay, I don't want to see this mesh. Okay, so just okay. So mesh wireframe model. I don't want to see the mesh. Display. Display. Here it's not working. Okay, anyway, select the face. So select this face, bottom face. Okay, face selection, bottom face, and insert fixed support. Okay, and also select this face, this one, and this face, two faces. Okay, these two faces, this face and this face, two faces, and insert hydrostatic pressure here, hydrostatic pressure. So cell phase should be here. Our coordinate is here. Okay, 0, 0 is here, 0, 0. So the fluid density, change the units, display units. Okay, meter cube. Fluid density is 1000 kilogram per meter. Water, fluid is water, and two faces. Cell face is top. Top means inside. Okay. So sometimes you will see the bottom. Bottom means outside. Okay, outside. So pressure is acting from inside, right? Fluid is inside, not outside. So that one is top, and defined by components. And x component is 0, y component is 9.8, acceleration due to gravity. Okay, 9.8 meters per second square. And so free surface location, y coordinate is, so from the bottom is 180 millimeter, right? 180 millimeter. So 0.18 we have to give. Y coordinate 0.18. Okay, so that one is hydrostatic pressure, boundary condition. And I want to solve for total deformation, and I want to solve for equivalent stress. Okay, and I want to solve for stress error. Okay, strain energy error. So that gives the accuracy of the solution. Okay, so solve. So this one is the solution. Okay, that one is stress solution, structural error solution, structural error. So very high value here at the bottom. So structural error should be 0. So this one is total deformation, 7.05. Okay, so yeah, it's like 7.05 e minus 8 meters. So very, very small. Okay, very, very small, because this one fluid level is just 0.18 meters, right? So because of that fluid weight, the pressure is nothing. And equivalent stress is 37,551. 37,551. So this one is not correct result. Okay, actually. So 63, around 63. 35, around 65,000. Actually, when we use 3D, this is the correct result. Okay, 66,000 you should get. So how to get the correct result? You have to modify the mesh size. Okay, mesh. So insert method and geometry, apply. And here I want to use all triangles method or multi-zone chord. Okay, so combination of triangles or quadrilateral, but triangles is better choice for curved bodies. So it's a very curved body, right? And element order, second order is automatically quadratic. So linear gives the less accurate result. Quadratic means more accurate result. Okay. And also I want to insert the sizing the same here. So select this surface, okay, apply. So element size is, so right now maximum size is 26, 2.6 e minus 2 means 26 millimeter. So I change this one, okay, change the units. So I change this one to 10 millimeters. Okay. Refine mesh I want to give, and update the mesh. Okay. So this one is little bit finer than before, and solve. And structural error, you see, very, very small, except here. Here is a mesh. Okay. This one is structural error, but that's okay, because the structural error is millijoules. Okay, millijoules. 1.118 e minus 6 means 1.118 e minus 9 joules. Okay, almost 0. And total deformation is like this one. That one is total deformation. And if you want to see the equivalent stress, MPa, I want to see the units in Pascals, 58,961. Okay, 58,961. Our cut result is 66 point. I used very fine mesh here. Okay, that's why. So this one is 66 point. So you can reduce further. Okay, you can reduce further element size. If you reduce further, you will get closer to our result. Okay. So body sizing, I use 0.005 and solve it again. So finer the mesh, longer the simulation time. And 67.259, you see, exactly same. And this is a deformation. Okay, so deformation. So that is how we solve using cell elements. Okay, surface body. The same problem you can also use a static structural. Okay, and engineering data is same. And I'm going to use right now, I'm going to use the 3D model. Okay, not surface, 3D model. I gave thick surface. Okay, thick surface, 4 mm 4 millimeter thickness directly. And yeah, let's see how it is imported. Yeah, this one is solid body, this one is surface body. You can right now we don't need this one, suppress body. Okay, we need only solid body. So because I created surface body first, right, and I give thick surface, and you can suppress this body. I don't want to see this body. And model, in geometry, flower vase, and mesh. Here I change the sizing for entire body. So default size is 19 millimeter. I changed that one to half, 8 millimeter. Okay. And insert fixed support. Yeah, here bottom is fixed, right? Bottom is fixed. Insert fixed support. Okay. And same here, this one and this one and this one. Inside bodies are subject, inside surfaces are subject to hydrostatic pressure. Okay. So insert hydrostatic pressure. Inside we have to select. And same fluid meters. It should be 9,000. Fluid density is 1,000 kilogram per meter water, and defined by components, and 9.8. Y component is 9.8, and y coordinate is same, 180 millimeter. So it's in meters, right? 0.18. And I want to solve for equivalent stress, and I want to solve for total deformation. Yeah, that's all. Solve. You take a little bit more time compared to surface body, okay? Because it's complete this 3D body, right? Yeah, this one is deformation, total deformation 6.8. So when we use a surface body, how much we got? 7.42. Okay, almost same. 6.8 E minus 8. Right? Here 7.4 E minus 8. So, and equivalent stress is 62,344. Okay, equivalent stress. So when we use surface body, how much equivalent stress? 67,259. So very closely matching, right? So I reduce the mesh. If reduce further, maybe we'll get both the results is almost same. Okay, that one is flower vase problem.